Hello, welcome to another Saturday session on complaining about Einstein's relativity. Just wait a minute, see if I'm turning up on YouTube. Yep, I'm on YouTube. Okay, all systems are go. So, hello, welcome again to this session. We're going to start complaining about Minkowski spacetime in this session. Minkowski spacetime was not in the original paper of Einstein in 1905, and it got added later. So, first off, an appeal for money. If you give us some money, we can carry on doing these Saturday sessions.
Hello, my name is David D. Hilser, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science, from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough, and that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear, and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
Hi, hello, and welcome back. So today's session is on Minkowski spacetime. So I'll try adding up the slides. All right, there you go. And the question posed is, did adding Minkowski spacetime to Einstein's relativity turn it into a different theory? Question mark. Next slide. So Einstein presented his paper on special relativity in 1905, and then in 1915, hold on a moment. Hold on a moment. Right, Right. I just turned the sound off of my other device. So 1905 special relativity, 1915 it was general relativity, and in between then Einstein was struggling to extend or develop special relativity to a more general theory. In that struggle, he seems to have discarded ideas which were not in the 1915 theory of general relativity. Ideas discarded seems to be variable light speed, question mark. And of course, in that period, Minkowski space-time got added to Einstein's relativity. So between 1905 and 1915, there was coming up with his ideas of treating time as a fourth dimension. And so that led to 4 dimensions, 3 dimensions of space and 1 dimension of time, to become called space-time. Einstein eventually adopted Minkowski space-time, but the way that he was treating light speed was not the same as how he was treating light speed in the 1905 special relativity paper, it seems, question mark. In Minkowski, it just becomes a conversion factor, ? This is the light speed. So light speed being treated differently when you go into Minkowski spacetime. And that's not how it was originally treated by special relativity in 1905, ? So Einstein changed how he was treating light speed as a constant ? It became just a conversion factor. It's a conversion factor of changing time into a sort of spatial dimension. Now this person, Unzicker, wants variable light speed brought back as how Einstein was treating relativity before 1915 and a bit after 1915, ? Should have put that more question marks up. So this is the person, it's Alexander Unzicker. So Alexander Unzicker is a physicist, and he's taken a more historical approach to looking at Einstein's relativity. He's looked into Einstein's papers between 1905 and 1915 and thinks that Einstein was trying to develop a variable light speed theory. And it seems to be that idea of a theory was discarded ? And Unzicker wants to bring back that theory. So the summary of the video, which I'm going to show, of Unzicker, it is, despite Einstein 1905 saying light speed, which is in vacuum, was a constant c, he was changing it into a theory of variable light speed, and that's Einstein. However, adding Minkowski spacetime changed that. So without Minkowski spacetime, it would have been a variable light speed theory, as what Einstein's really advocating. So I'll bring what I think into it. From my perspective, it is discarding the light speed constancy postulate, NB. That postulate is ambiguous, vague anyway, that's in my view, and going back to variable light speed is consistent with Newtonian physics. So we should view relativity principle also from Newtonian physics context. Thus, all of this, in my view, is a return to Newtonian physics. But I have the basic idea there is a mistake that's being made by having the Newtonian paradigm restricted by light speed c, and it's given the false Newtonian paradigm, and then having need for speeds greater than c arising, and so get around that by adding extra ideas or assumptions to relativity point of view of space expansion being allowed greater than c. So it's all being built on the false claim that Lorentz transformations reduced to Galilean transformations at low speeds. That's a good approximation. So the whole paradigm, the whole structure of Einstein's relativity got messed up, when the correct Newtonian paradigm has no such restrictions and it allows speeds greater than c. So that's the finish of my little introduction to this video that I'm now going to play from Unzicker, where he's giving his views on Minkowski space-time. And then after showing the video, we can open up to discussion.
Go fast, go lightning fast with our reliable network. Just £29 a month, no setup fee.
Good morning, everybody. Thank you for coming. I like to be at the history section because it's a well-known cognitive illusion that the human mind is focused too much on the present. And so we're all overestimating the current events, and that translates into physics in the sense that we are too much focused on what is happening today, this year, on big conferences, and we're not considering enough the history of physics and the long-term developments. So I would like to emphasize this important point of physics. And, well, my title is Why Minkowski Led Physics Astray. And I would like to jump into history in 1905, when Albert Einstein formulated the special theory of relativity. You all know about this. And it's important also the contribution of Henri Poincaré, which is sometimes a little bit neglected, but he made significant contributions to the special theory of relativity. And interestingly, if you look here at the details, Henri Poincaré was actually the first one who introduced something like a four-dimensional metric, and the first one who introduced the imaginary unit, who attached the imaginary unit to the time scale. And he had the idea of a four-dimensional reformulation of this mechanics. But, well, interestingly, he said, because in his opinion, the translation of physics into the language of four-dimensional geometry would entail too much effort for limited profit. That's Poincaré. And, you know, but this point of view, this four-dimensional formulation has become very important and very influential. And Minkowski promoted it. And so we might ask, I mean, how did this happen, this really huge influence of Minkowski on the mindset of physicists? And actually it goes back to one famous presentation at the meeting of the Society of German Natural Scientists and Doctors in 1908. And you should know that it's the oldest scientific society in Germany, founded in 1822. And it had a very big reputation. And you see also the title is already something spectacular, two simple words, and it appears that a new era of physics opens. And of course, Minkowski was also from Göttingen, a famous mathematician with a famous tradition. And but if you look at the content, the equations of Newtonian mechanics are invariant in two senses. Firstly, their form is preserved when the underlying coordinate system undergoes any change. Secondly, by change in position and change in rotation. Secondly, by altering it in its state of motion, imposing some uniform translation on it. That's basically Lorentz invariance. I mean, Lorentz invariance is a remarkable property. But it's in that sense nothing new. And well, Minkowski postulated what he said: 300,000 meters per second is 1 second in the imaginary unit. That's basically setting the speed of light equal to 1. That was his idea. He called that world postulate. And that's how he commented. The unquestionable validity of the world postulate is the essence of an electromagnetic world picture invented by Lorentz, further developed by Einstein, that has now become obvious. That's not a too modest statement, is it? As the mathematical consequences evolve, those who are reluctant will find relief in the idea of a pre-established harmony between pure mathematics and physics. So, one might wonder about the relation of physical content and public relations. And it's formulated in a very poetic language. Let's see if I can go back. I think I skipped that before. But he phrased his findings in a very poetic language. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. And all this is nothing else but, well, stating that there is Lorentz invariance, if you want to look at it soberly. So, I think, I mean, considering the huge influence of Minkowski in today's thinking, in today's paradigms of theoretical physics, we are well advised to wonder about the content of poetry and the real physical content in his findings. And that's his statement of the new era. And of course, he came from a famous tradition in Göttingen. Göttingen was the university of the most famous mathematicians, David Hilbert and Felix Klein and Hermann Minkowski. And also there, I don't want to give all the blame to Minkowski, but also there was the origin of the idea that further progress in physics could only be established by, well, inventing new mathematics and by considering purely mathematical relations, which I think is at the long run misguided. But everyone talks about Minkowski spacetime. It's really at the very basic education level in special relativity, as it was a necessary part. And Julian, yeah, I mean, just to summarize the findings, I mean, what he did, I mean, he did reveal some mathematical properties which are intriguing of special relativity, such as the four-dimensional distance and the negative distances interpreting the generalized rotations, that Lorentz boost can be seen as a rotation in four-dimensional space. That's all very nice in the concept of a light cone. His ideas had an enormous influence on the paradigm of theoretical physics, and they are seen as an essential element of special relativity and also general relativity. I would like to question that, and of course, Minkowski's influence was also that he encouraged physicists to think in higher dimensional spaces. That was the first step from 3 dimensions of reality to that 4th dimension. And I'd like to quote the historian physicist Julian Barbour, the author of the book The End of Time. And he correctly noted Hermann Minkowski's ideas have penetrated deep into the psyche of modern physicists. I would like to add, maybe by bypassing reason a little bit, because it's not, if you take a sober look at the facts, it's not really new content what Minkowski had developed. And even Einstein was a little bit reluctant. He ironically commented, since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore. But that was a little comment, but Einstein did not actively oppose to the 4-dimensional formulation of this theory. And, well, what's physics? Physics is about pondering deep concepts. Nothing is created by coincidence. Rather, there is reason and necessity for everything, as the ancient philosophers said. And I think we have to ask the basic questions. And one of the basic questions is, how justified is this union of 3-dimensional space and 1-dimensional time? And it turns out that there is no real justification besides that postulate by Minkowski, I mean, space and time are simply different phenomenologies of physics. And gluing them to a four-dimensional space-time is, well, at the very end, nothing but a denial of reality. Okay? Just lean back and think about, is space and time really the same thing? It's not. But this argument, I mean, it's this central argument of mine. It is so simple that you might easily dismiss it and say, okay, if it's such a simple thing, why haven't physicists thought about for 100 years? But on the other hand, I think it's precisely the problem of theoretical physics for almost 1 century that it has given up pondering deep physical concepts in favor of playing with mathematical formulations. Okay? And this is an unsolved problem. It's still on the table. There is no reason why nature should show its four dimensions in such a peculiar 3 + 1 dimensional manner. There is no mathematical reason. Okay, so you can't just treat it as something 4-dimensional and say, okay, there is a little conversion factor. Don't mind. We don't worry about. And I also think that strips off that kind of thinking strips off the fundamental meaning of the speed of light, because the very existence of the speed of light tells us something about reality. Okay? There is no a priori reason why something as a limiting velocity should exist in nature. And people should wonder about these concepts. And I think Minkowski's paradigm was, well, helped a little bit to dismiss and to belittle the importance of this speed of light. So one of my favorite quotes of Erwin Schrödinger, and a little bit another context: once a problem is removed by a feeble excuse, there is no further need to ponder over it. And so now let's continue history. Einstein, after having formulated special relativity in 1905, continued with general relativity. And you might think, well, general relativity is 1915. No, the very first idea about general relativity, the key idea, so to speak, was the principle of equivalence in 1907. And he developed the idea that light should be deflected in a gravitational field as it is obviously deflected in an accelerating frame. And that was 1907. And another, interestingly, the immediate idea of how to resolve that, how could possibly a gravity field, how could it possibly bend light, was, okay, let's think about a variable speed of light. Let's think about a refractive index like in optics. And that's what Einstein published in 1911. And this is strictly speaking not related to Minkowski, but it's a very interesting formulation of general relativity, which I think could have more importance. But I mean, if you take the mindset of Minkowski and that 4-dimensional formalism, you're not thinking in this terms of variable speed of light. It's a little bit two different paths that had opened back then, one formalistic mathematical formulation and the other one more intuitive of variable speed of light. That's what Einstein said in Prague: from the just proved assertion that the speed of light is in a gravity field is a function of position, it is easily deduced from Huygens' principle that light rays propagating at right angles to the gravity field must experience curvature. And interestingly, Einstein's idea included Mach's principle. He would have been thrilled had he known about the size of the universe back then. It was 1911. Just remember that the size of the universe was discovered around 1930. And Ernst Mach was also a profound thinker of gravity. And I think in a certain sense, you could see in him an antipode to Minkowski. Minkowski represented the mathematical formulations in 4 dimensions. And Mach, maybe he was not such a brilliant mathematician, but he had very relevant ideas about the origin of inertia and the origin of gravity, which I think are underestimated to this day. And so, but yeah, maybe just history took the wrong path back then. I have other talks about this theory of Einstein in 1911, which was the first variable speed of light formulation of general relativity. There is also a very interesting relation to Dirac's large numbers, which I'm not going to mention in detail now. And however, all this is a quite interesting picture, not only historically, because all these people had very ideas that are very close together. Erwin Schrödinger's thoughts about cosmology, Dirac's large numbers, Mach's principle, Einstein's variable speed of light approach, which was rediscovered by a British cosmologist later. And first of all, maybe Robert Dicke, he also had a variable speed of light formulation. I think this is a very underestimated possibility how one could formulate general relativity, but it's very contrary to the 4-dimensional paradigm which had been established long before. So, I mean, Minkowski is not the only guilty one. Einstein got in contact with Marcel Grossmann and learned the geometry of Bernhard Riemann from Marcel Grossmann when he moved from Prague to Zurich in 1911. And so he started to look closer at this geometrical formulation, which you can do, of course, but it's just two sides of a medal. You can either formulate it with metrics and connections and curvature, or you can formulate it with variable speed of light. And this is not well known, and you might look at this statement of Einstein in 1913. The speed of light is no constant, but depends on position. Therefore, one is forced to generalize the theory of space and time known as relativity. And so you might think that he gave up this variable speed of light thoughts in 1915, when he came up with the tensor equations of general relativity in Schwarzschild's solution. But look at this. In 1917, a curvature of light rays can only occur when the velocity of light varies with position. So Einstein obviously did not dismiss this variable speed of light point of view. So even if he became famous in 1919 when Eddington presented his legendary results from the excursion and at the Royal Society in London, New York Times headline the next day, big revolution in physics in 1919. Newton is dead, we have a new hero, Einstein. And this was the moment where the geometric formulation was really established. And you might think, well, Einstein gave it up later. No, in 1920, he still wrote about the other possibility. This consequence shows that the law of constancy of the speed of light no longer holds according to the general theory of relativity in spaces that have gravitational fields. This is 1920, okay? And he continues, as a simple geometric consideration shows, the curvature of light rays occurs only in spaces where the speed of light is spatially variable. From this, it follows that the entire conceptual system of the theory of special relativity can claim rigorous validity only for those space-time domains where gravitational fields are absent. Okay, so this is just a small summary of this variable speed of light version of general relativity, which is in contrast to the Minkowski point of view. Variable speed of light was Einstein's initial idea in 1907. It's determined by the distribution of masses in the universe. That's the very Machian idea behind the change of D is hidden by the simultaneous contraction of measuring rods. Of course, you always measure this very same velocity of light, because if the speed of light changes, the wavelength and the frequencies change accordingly, so that you can even define, as it is done today, C as a constant. Very interestingly, it's just an elimination of the gravitational constant by construction. It agrees with Dirac hypothesis, and there are interesting cosmological differences, which I'm not going to deepen today. Let's get back to Minkowski. Did Minkowski's concept really help to develop general relativity? I think no. The four-dimensional formulation rather obfuscates the variable speed of light concept. There is another line of argument I'd like to briefly touch. I think physics does not wander enough about fundamental constants, about constants of nature. And you have an interesting statement, a later statement of Einstein here. Numbers arbitrarily chosen by God do not exist, and their alleged existence relies on our incomplete understanding. I like this statement because it emphasizes that you shouldn't take constants for nature, you shouldn't take them for granted. You shouldn't just believe them as God-given numbers and work with them. You should ponder and stop and explain their very existence sometimes. So there is another talk on Thursday about constants of nature, the Road to Fundamental Physics, where I would like to deepen this, but I can briefly lay out the idea. If you look at history and look at scientific revolutions, what's the first step? The first step is not mathematics. The first step is always a visionary idea. And then in the second step, you have a mathematization, you have an important equation, and in the end, you have always a reduction of the number of constants of nature. Now, this sounds quite abstract. I give you 3 examples. Take Newton's law of gravitation. Okay, you have this inverse squared law, which is fantastic and worked out in decades of mathematical pondering, but the very revolutionary idea is the first one. Mundane and celestial gravity have the same origin. That's the unifying concept. It sounds very simple to us today, but in 1687 it was not. And if you look what happens then, I mean, think at the time before Newton, if you measure local gravity, okay, how fast things are accelerated. This could be considered an important constant of nature. That tells you something about nature, how fast, how strong gravity is, okay? But once you have understood Newton's law of gravitation, this little g, this local acceleration, becomes totally irrelevant. So it's one just on a little planet, and it depends on the mass of this little planet and the distance and of this universal constant. But this is the important constant. This has become irrelevant. This has become eliminated by that equation. Another example, entirely different field, look at electrodynamics. But what's the big revolution? The big revolution is, oh wow, light is an electromagnetic wave. Okay? That was, by the way, the first idea by Weber. And then came Maxwell, and of course he had the formulation, the mathematical formulation with Maxwell's equations, eventually coming out with this very, very important relation that says, okay, we have electricity, we can measure it, we can measure magnetic constant, and we have the speed of light, and these are related, okay? And the essence of the revolution stays in the fact that you're eliminating one constant of nature here. You had 3 constants of nature independently, if you don't understand the connection. And once you understood that light is an electromagnetic wave, you have only 2. That's the big progress. Again, another field, thermodynamics, and, well, the revolutionary idea of Maya was temperature is nothing else but kinetic energy, okay? So have a little mathematization and look at this. I mean, this could be considered an important constant of nature, later called Boltzmann's constant, but once you understand, so it becomes a totally irrelevant number that defines just the temperature scale, okay? So my point of view is when you have revolutions in physics, look at the constants of nature, and in every revolution there is a reduction of the number of fundamental constants. And well, did Minkowski explain the existence of a C or even a finite C? No, he did not. To the contrary, his views help to dismiss the fundamental importance, because if you look at the history of physics in this way, you end up at the very end with questioning or wondering about the very existence of C. Why is nature built in such a way that you have certain constants that you can't get rid of? We've been able to get rid of a couple of constants, epsilon 0 and so on, and Boltzmann's constants, but there are some constants still remaining. But I think if we want to do real progress, we have to eliminate or to explain these remaining constants. One of them is C. And this is again touching another talk of mine on Friday. Every constant of nature is something like an anomaly in a sense of the science philosopher Thomas Kuhn. He said, whenever an anomaly appears, that means something is wrong. And I think at a very long time scale, we are talking about 400 years, you could look at the velocity of light as an anomaly. There is no reason whatsoever from Newtonian physics that tells you that accelerated masses should have a limited velocity. Why? There's just no reason. So if we stumble upon an anomaly, we shouldn't just declare it irrelevant and the constant of nature and digest it. We should ponder it and ask for the reason of the very existence. And at the very end, that casts doubt of on the very concept of space and time. More on that on Friday. And well, to conclude, is the book of nature written in mathematical language? Yes and no. I mean, I think that today there are obvious degenerations of science, like conferences taking place a couple of years ago here in Munich, scientific methodology in the absence of empirical data. That basically means scientific methodology without science. I mean, that to me is kind of obviously ridiculous. And you can you can just randomly pick out one of these 10,000 papers and multi-Galileons and higher co-dimensional brains and 5-dimensional bulk with Lovelock terms and 3-brain and so forth. I mean, you know, I just picked this out because it's kind of funny because they refer to Galileo. I mean, they are inventing all kinds of particles, but they are referring to Galileo. And Galileo said, I don't feel obliged to believe that the same God who has endowed us with sense, reason, and intellect is intended to forego their use. But that's just a sideline. I'm going to finish. Is the book written in mathematical language? Yes, I'm not arguing against this. I think there are very interesting things. And, well, to conclude, for the space-time, that's basically all what I said. There is no good reason for why nature should behave in such a peculiar three-dimensional manner. I think we should ponder that. And you find more about these ideas in this publication in Annalen der Physik. I developed the Machian version of Einstein's relativity. This is about the origin of constants C and H. And this is a popular book about the fundamentals of physics. There's also a YouTube channel. And this is maybe the closest book to the ideas I was presenting today, Einstein's Lost Key, Why We Overlooked the Best Idea of the 20th Century. I think that Minkowski has contributed a little bit that physics has gone off the rails. Thank you for your patience, and I'm happy to have some questions.
Hey, hello. Hello again, back again. Hi. So hopefully you enjoyed all that. So add in Minkowski space-time to Einstein's relativity and might have messed it up. But of course, there's lots of problems with Einstein's relativity. And as you read it, you find that there's lots of problems. But adding Minkowski space-time might be another contributing factor to making that mess. So, is there anybody wanting to ask questions? I see Franklin there, John, Vladimir, Dennis in the green room. Okay. So I go to the comments. I call up some comments from people who've been watching this. See what they've been thinking. So, first off, people wondered what happened last week, and there's problems. We keep finding things about StreamYard we didn't really understand, and it ran out of memory. And so there's been a few comments going backwards and forwards about that. So we seemed to max out on the memory last time. Let's see the next comments. So it's weird that physics uses space-time as a thing to do things. Yeah, so it all comes from relativity. Space and time are not things. It's sort of like philosophical. So light speed depends on levels of matter, maybe. I don't know. Right. Oh, we got a comment here by Franklin. The speed of light varies in gas, water, and air. It was never constant, like the number pi. Yeah, it's only constant regardless of the speed of the transmitter. Yeah, maybe. So Einstein was considering a variable light speed, and it might have gone in that direction. But it got muddled up by introducing Minkowski spacetime. The boiling of water is a constant, isn't well. Supposed to be the temperature. Referring to the sapphire experiment, and that's not something we're talking about. The light speed on any of the next systems will be the same. Subatoms, atoms, so forth. Don't know. Speed of light varies through different media, yes, but this is not a vacuum nor a gravitation-free environment. Yeah. So it says constant, so I lie. Okay, maybe. Charge takes one charge particle. Don't know. I don't know. Not really seeing anything commenting on the video. I see. Yeah, so the chat has gone off on a diversion talking about plasma. Normally, he says maybe. Okay. Fine. Still, what I'm seeing is still talking about plasma. Frankly, in fact, it says, I don't think Unzicker said much other than the space-time is junk. Yes, well, he didn't like, Unzicker didn't like space-time. And he was pointing out that it was changing the meaning of what light speed was. It was a conversion factor in Minkowski space-time. And then what Einstein was talking about in his 1905 paper on relativity didn't seem to be treating it as a conversion factor. Space and time can't be combined. Well, probably Unzicker would have liked them not to be combined. Yeah, two separate things. But we're sort of the using C as a conversion factor. Right. Shockwave. Light slowing down through a medium and then speeding up is akin to electrons speeding up on it way to the heliopause. Maybe. Okay. What's this one? Okay. Light speed never will be the same in an atom and so forth. I don't know. Let's see. An atom cell or star will never be a gravity-free vacuum. So, of course, light speed varies through them. Yeah. In between neutron and electron, there must be a neutron to mediate the charge. Okay, so I think most of the comments have gone off on a tangent, talking about other things. Kept to the points that Unzicker was bringing up in this video. This is about the construction of Einstein's relativity. Einstein's relativity, 1905, did not seem to be treating light speed c in the same way in which Minkowski was later treating it. And so incorporating Minkowski space-time into relativity seems to confuse things. And without it, maybe it would have gone in the direction that light speed should have been variable. And sort of like the papers that Einstein was writing seem to say that light speed was variable. But one of the issues I find a problem with is in the German, the word velocity and speed can get muddled up. So when Einstein was saying, which actually quoted was that variable light speed was, variable light velocity was being said by Einstein in 1917. Was that really supposed to mean velocity or speed? Because velocity is speed and the direction. So if you've got constant light speed, it can still change its direction. So you've got constant light speed, direction can change, and that means you've got variable velocity. So you can have variable velocity and constant light speed. So when Einstein starts talking about constancy of light speed, is that really supposed to mean constancy of light velocity? I think there's a confusion in the German when it sort of gets translated into English. So what Einstein is saying is subjected to a bit of confusion on that issue. So is anybody in the green room wanting to make any comments? Anybody want to hold their hand up? Hey, Dennis. Okay.
I just wanted to make the point that Martin Speer's electrostatic capacitance theory of gravity derives Newton's gravitational constant in terms of epsilon naught, the electrostatic constant, and the speed of light.
Sorry, whose theory was that?
I beg your pardon?
Yes, sorry, whose theory was that? Was that Unzicker's?
It's correct, because Unzicker said that revolution would involve eliminating at least one constant in terms of the other constant.
Yeah.
And Spears does that.
Okay. Thank you. So you think it should be a variable light speed theory that Einstein's relativity went wrong when it decided to have constant light speed, and really it should be a variable light speed theory, do you think?
Well, I haven't taken a position on whether light speed should be variable, and although I think that Ian Cowan has shown that there's a I'll put this in, this is from here he suggests an experiment to show that light speed is variable. This is Ian Cowan. But Spears, I don't think, took a position on whether it was variable or not. He just pointed out that you could derive Newton's gravitational theory from the electrostatic theory of Coulomb, and the speed of light, the speed of light comes into it. He didn't use any magnetism, but he used the electrostatic and capacitance theory and derived Newton's universal constant of gravitation through that derivation.
Okay, thank you.
You're welcome.
Yeah, thank you. So anyway, with Unzicker, he's developed his own theory based on reinterpreting the papers of Einstein, and he thinks, if I put on Unzicker's point of view correctly, he thinks it should have gone the direction of variable light speed. Okay, thank you. Okay. Next, anybody else? I'll be moving in ahead. Yes, thank you. Anybody else put their hand up? Let's see. Going down. Yes, we got 3 down here. So, who put their hand up first? Who's first? Nick? Oh, I saw you first, Nick. Hi, Nick.
Hey, Roger.
Hi.
Thank you for bringing that video of Unzicker to us. I thought it was really packed through a lot of great ideas.
Yes, I thought so too.
For example, he mentioned that a lot of the big positive paradigm shifts in science eliminated a constant. So if you want to reverse engineer to a great paradigm shift, you look at constants and say, okay, look, which one looks like it can be eliminated, and come up with a paradigm shift to eliminate that constant. That's very thought-provoking, and there were quite a few other really good comments in there.
I made a note.
Yeah. So I'll probably watch that one again.
He said 4D. Yes, he said 4D space-time is a denial of reality. He said lots of interesting. He said lots of interesting things.
That main topic, I thoroughly agree with. Yeah. This is perhaps a little off topic, but my focus was special relativity, and in particular, I engaged in a lot of debates with relativist professors about the twin paradox.
Yeah.
And in there, they would often use Minkowski diagrams to reconcile the twin paradox with special relativity, or alleged to do so. But my experience was that basically the same rebuttal that I used for the Minkowski explanations were used with his diagrams. So it seemed to me that the diagrams were a very straightforward graphical interpretation of the equations, the math equations in special relativity. So I think that 4D space-time is kind of baked into special relativity. And it's unfortunate that that baked in space-time got carried over to general relativity. So, so to me, again, just repeat that I think of Minkowski diagrams as simply a graphical representation of what is actually said and implied by length contraction and time dilation in special relativity. And that's just one more flaw in special relativity that got transmitted and put on top of the general relativity gravitational equations.
Yeah, on the Einstein 1905 was not talking about Minkowski space-time. So he's talking about things differently. So then they add Minkowski space-time to it. And that seems to change things. So when they sort of like use Minkowski space-time to solve the twin paradox, it seems to have changed what Einstein was originally talking about in 1905, because the Minkowski space-times, to my mind, seem to introduce a preferred frame, and the principle of relativity is saying there's no preferred frame. So suddenly, 1905 paper, no preferred frame, then add Minkowski space-time, and then they're changing it, and they're sort of like, that's bringing in a preferred frame. And so it's what I call moving goalposts. They're sort of like, they just keep moving things on. It's sort of like, well, you're not talking about the twin paradox in the original context of what Einstein was talking about in 1905. You've sort of like moved it on to what Minkowski was talking about in 1908. So they're not sticking rigidly to definitions of terms and so forth, and they're moving the goalposts, moving things on from what was originally said to something else, and not making it clear that's what they've done. And so it's just making a terrible mess.
That's a good summary.
That's my gripe about it. So Minkowski space-time, when that got added to Einstein's relativity, as sort of like what Unzicker was pointing out, well, that seems to change things about what Einstein was then later on saying about variable light speed. It's sort of like, well, they haven't got everything, the mainstream haven't got everything connected in properly together. It's just a confusing mess of things which don't really fit together properly. Okay, thank you.
One more point, and that is Unzicker brought up the equivalence principle
Yeah,
as sort of the explanation for curvature of light. But
yeah,
Ron Hatch, the expert on GPS data, says that the GPS data disproves the equivalence principle. And he wrote quite a bit about that. So that's another point.
yeah.
So thank you very much, Roger. Very
All
interesting.
right, thank you. Thank you. Cheers. Thank you. I'll remove you now. Let's get who else has got a hand up? It was Franklin. Do you want to come on? Oh, John's back as well. I'll put Franklin up. Hi. Hi. Hello.
Hey, Roger.
Hello.
So that was quite a long video, 30 minutes.
That was
You know,
long,
I
was it?
already made my comment that, you know, he's basically just saying that he doesn't like space, time, and its concept. You know, he really didn't go into like what the consequences of Minkowski's theories were, other than he's just said there was no, you know, theoretical justification for trying to combine these two things.
Yeah.
So I was a little bit disappointed in that. I mean, he should really explain.
He did do his adverts at the end about for more read my books and so forth. So it was supposed to be an introduction as far as he was concerned, because I think he's promoting his theory of variable light speed.
I mean, your topic here was whether Minkowski turned special relativity into something different.
I know, but for Utzinger, he's advertising his theory. He's sort of like, this is introduction into his theory. He's distributing Minkowski space time. He's saying things like 4D space time is a denial of reality, and it's looking at the light speed c in a different way to what Einstein was originally talking about in 1905, Einstein's 1905 paper, and it doesn't seem to connect properly with what Einstein was later saying about light speed being variable.
Well, do you think it did that? I mean, did it? I mean, I thought it was interesting the quotes from Einstein saying that, well, the only way light can bend is if it has a variable light speed, right? So, but he seemed to be like surprised about that. I mean, I've always said that that shouldn't be a surprise, because obviously the speed of light is not a constant. It's not the same. It depends highly upon the environment upon which it is traveling. You know, one of the comments was that light can be slowed down 5,000 times. You know, so it's obviously not a constant. You put light through various mediums like glass, you get refraction. That's obviously due to it slowing down.
Yeah,
and that the original special relativity paper just merely said, actually never said that the speed of light is a constant, but that it doesn't change with respect to the transmitter speed or the receiver speed, which is something which is, you know, highly unusual, because if you thought that light was like a particle and you launched it off the front of a train, you'd think it would take the velocity of the train. But we don't see that. We see that the speed of light from the light bulb at the front of the train travels at exactly the same rate as light that was transmitted from on the stationary ground, right? That is the constant that is the true constant of special relativity. Not that the actual absolute speed is the same, but rather if you have one source which is moving and one source which is the same, and you transmit light at exactly the same time, that you'll see the wavefront travel at exactly the same distance after it left the transmitter. Even though this one might be going 1,000,000 miles an hour, this one might be going 1 mile an hour. It's when the light comes out, it travels at the same speed as measured by if you were able to observe the wavefront, you know. And that's because when you're measuring speed and stuff like that, that's another problem. But observationally and geometrically, if you can see that there's two runners and they're both going the same distance at this over the same amount of time, you would say that they are running at the same speed, and that speed could be said to be a constant, right? So I think people just really getting their axles wrapped around this whole constant thing. But my emphasis is that it's not a constant in the sense of like, pi being 3.14. That's a constant. That does not change. It's
that pi is a constant in a flat space time, but then when you got curved space time, it's
still a constant. Pi is pi. It's a number. Just like
the circles. If you draw a circle in flat space time, you're all right. But if you draw a circle in
let me
curved
just
space time,
make
then
it
it
even
gets
clearer.
confusing.
Let's say like the number 7 is constant, right?
Yeah.
Okay.
Yeah.
The number 7 is a constant, right? It does not change. It represents the same thing at all times and all places.
Yeah.
Light is not such a thing. Like my comment, I said that the speed of light is similar to like the boiling point of water, which varies depending on your atmospheric pressure, right? But it's like the speed of light in that I could say the boiling point of water is independent of the starting point of your water. So if your water was at 40 degrees, it will boil at 212. If it was 90 degrees, your water will boil at 212. So the boiling point of water
when they define something like that, when they define something like that, they define it as standard temperature and pressure. So they're talking about the boiling point at a standard temperature and pressure. And
well, they have to say that. I mean, you could say the same thing about the speed of light, which is in vacuum, without the presence of gravity, that it travels at this,
the speed of light. About the speed of light, it really should be traveling in a perfect vacuum, but you don't really have a perfect vacuum. It's sort of like,
but that's the only way that any two scientists in the world can run the same speed of light experiment and come up with basically the same answer, right?
Yeah.
But if you perform the same experiment on, say, the moon, you would get a different number. Or if you perform the same experiment on Jupiter, you would get a different number.
Yeah.
But that has to do, which was not touched on at all by Unzicker's video, which was that this whole space-time thing actually had to do more with general relativity and the introduction of gravity and trying to justify how gravity creates its forces. So
between what he was dealing with is between special relativity in 1905 came Minkowski space-time, and then came general relativity. So it was a development
I was thinking
process.
that Minkowski's extensions really, I'm not convinced that they really changed, say, special relativity, but it was more of an influence on general relativity, where we started coming up with these, you've seen the classic gravity well demonstration where they take a rubber sheet, they put a bowling ball in the middle of it and say, this is how gravity works, right?
Yeah.
Which is completely stupid, because if you were to put that experiment into, say, a gravity-less environment like the International Space Station, you would find that doesn't work. I mean, even if you pulled the bowling ball down to create the dimple, you would find that the ball would not roll around and demonstrate gravity. The only reason why that works is because you're using gravity. You have to have the force of gravity present in order to demonstrate gravity, thus showing that it's a completely circular definition, which is actually just complete nonsense, right?
Yeah.
This whole thing about incorporating time into space is supposed to distort space in such a way that, for example, it creates a rolling downhill, which once again requires the order for that.
Doing space time, when space time bends and all that, the particles and that matter and all that supposed to follow the paths of that bending in the space-time. But
Yeah, that's
so
what
when
they
you
say.
do the gravity well experiment, when you really have got gravity and you're deforming some fabric using actual gravity, that doesn't really. That's only an analogy. It's not a metaphor. It's not really what space-time curvature is, but they do use it. Yeah.
Best, it's a really, really bad analogy. Really.
Yeah.
It's and a really bad one. I mean, it doesn't make any sense.
Yeah.
I mean, the thing about space-time is that, well, sure, maybe it can explain why a satellite can go in a circle because it thinks it's going straight, which is the typical explanation. But of course, if you stop the satellite, then it just drops straight to the ground. And that is not at all explained. Why is it that you take your satellite and you just stop it in the middle of space? Now, it doesn't matter how distorted your space is. If you stop something so it's not moving within that space, it has no incentive to move in any direction, right? It's just going to, obey Newton's law, and it's just going to stay there. So if gravity were,
when it's an object moving in space-time,
when I look for this calculator, it should remain right here, right? Unless I move it forward, would you be able to see?
You're resisting the space-time curvature. A particle that's object free to move in the space-time curvature, that's the path it's going to take. And then if you're going to try to resist that by using a propulsion or something, that's making things a bit different, isn't it?
No, it's just complete nonsense. It's completely nonsense. General relativity is essentially saying that force is gravity is not a force. It's the result.
Some people say that,
of time, right? This is,
sorry.
I think, the biggest impact of a Minkowski space-time is that people say ridiculous things like that. Gravity is not a force.
Yeah, some people say that.
Of the bending of space and time to create, these gravity wells, which I explained, only work in the presence of actual gravity. So I don't know. It's just complete nonsense. But
this is part of the building process, because Einstein wrote his paper in 1905. Minkowski came up with his ideas, and other people came up with their ideas. And Einstein eventually develops general relativity in 1915, and things just keep carrying on. It's all sort of a development process, and sort of like this is what we've been talking about. Really, has been dealing with the development of relativity from special relativity to general relativity. And if you want to, there's a lot of other baggage that comes after that and during that.
But getting to your original point, I mean, do you think that the special relativity was modified by space-time in any significant manner, or did it just evolve into a completely different theory, which is like general relativity, right? It didn't really touch.
The connections, I think people have pointed out the connections from how do you get from special relativity to general relativity is not very clear. I think people have pointed that out. If you go back to the original paper in 1905, special relativity, the light speed c seems to be used as a way of synchronizing clocks, and then Minkowski is using c as a conversion factor for converting time into a spatial dimension. So you've got
I don't understand that conversion factor thing. I mean, why would that be a conversion factor?
Well, you got the Minkowski space-time metric, and it's x squared plus y squared plus z squared minus c squared t squared, and that's the metric for it. So you then treat in time as if it was a dimension, the fourth dimension, and you're then treating it like a spatial dimension by multiplying time by c. So it's not quite what Einstein was talking about in 1905. So how does it get from what Einstein's talking about, light speed and in 1905 to what Minkowski was then talking about, it doesn't really seem. How do you get there? It's sort of.
Well, it seems like, I don't know, completely unrelated, really. I mean, and mathematically, you can do all kinds of crazy things. Like you can mathematically calculate into any arbitrary fourth dimension. You just multiply by another factor.
When I was first, this is more than 20, 30 years ago, when I was first looking at relativity after being taught it, I thought, wow, time fourth dimension. Let's make a fifth one. Let's make mass into a dimension of space. So I was going off looking at a theory like that, where mass is a dimension of space, matter. So you use a conversion factor of the capital G and some other factor to multiply mass by, and then you retreat in that as a spatial dimension.
Well, you can go to 16 spatial dimensions, and then you have string theory.
Yeah, string theory. String theory is 10 dimensions, so I was trying to connect it into that as well.
Me personally, I think whenever you've gone off of more than 3 dimensions that we can observe, you have run off the rails, which is what physics is.
We don't experience time as a spatial dimension, but we do experience time.
It's definitely there. I mean, you have the video saying things like, space and time, they don't exist, right? It's like really obviously wrong stuff, right?
Well, no, it's how we experience things, and then how we experience things doesn't necessarily the same as what the mathematics is. So the mathematics, you got the mathematics, and then there's conversion of how that mathematics connects into how we experience things.
Yeah, I would just finish by saying, that's all crazy, man. That's crazy talk. And they think we're crazy.
Yeah, there's something about some joke, isn't there, about a mathematician who was playing around with his equations and mistook his equations for reality or something. So
yeah, it's no reality at all. So,
so another one was about a mathematician writing about how to increase milk production for cows, and he starts the paper by saying, "Consider a spherical cow."
Yes,
you start your mathematics by considering what would be the milk production if the cow is sort of like a balloon. Oh well, that's the way it is. Thank you, Franklin. So I'll bring up John now. Thank you. Here you go. Next. Oh, okay. Hello, John. Hi. Hello.
Hi, Roger.
Hi, thank you. Cheers. Welcome here.
Yeah.
John. Hopefully you've got your problems sorted out from last time, have you?
Yeah, well, so it seems so far.
Good.
I've gone now, an hour and a quarter and still on.
Great. So excellent. So we keep finding problems with StreamYard because we don't know what we're doing with it. Sort of last week.
But I took your advice.
So yeah.
I took your advice. I'm now talking to you on a Windows 11 new computer, hardwired into the modem.
Yeah.
Meaning, the RJ45. And this seems to work. So far, anyway. Anyway, like your topic here, to me, what Minkowski brought to physics was the idea that you start with math and then see what happens with the physics. Math first. I mean, that's what he was doing. He was monkeying with parameters and making the parameters kind of match, right? Remember, in math, a dimension is just another parameter, then linking it to whether it's time or space in physics was the second issue. And even today, it's math first.
Mathematics.
If you notice math first. If you notice in Unzicker's presentation, he said in physics, first you start with an idea.
and that is an idea to change the math, and then down the road a piece or a couple steps, you end up trying to look around and see if anything is being described. That's math first. And I would suggest that you do it the other way around. You start with some observation that doesn't quite work, and then try to figure out why it doesn't quite work. You know? So there's plenty of examples of that.
I don't think so. I think if you go back to Galileo, who's the foundation of modern physics from the Renaissance and so forth. I think Galileo, he pointed out that mathematics is the language of science, physics, what we now call physics. And if you're sort of like going to measure something like speed, then you've got to say that speed is equal to distance traveled divided by the time it takes. So by doing just something like that, you are introducing mathematics. You've got to define some mathematical concept before you can get out to measure something.
Well, yes, but even Galileo started by rolling balls down an inclined plane.
Yeah, and he needed the concept of speed.
And then he come up with the math.
Yeah, you needed speed. So you needed distance traveled divided by time taken, and that's a mathematical concept. So he started measuring something, and so you're measuring something, you have to define the mathematical concept for it.
That's right. That's right.
Yeah,
that's physics first.
So
observation.
And then if you go back to further into the Greek philosophers, then the great man himself, Pythagoras, then it's sort of like it's mathematical mysticism, where you got the music of the spheres and what Pythagoras was noting was the sort of like mathematical relationship between music, and so he was considering mathematics as being how the universe was operating by this sort of music. So it's a long tradition of thinking the universe operates by mathematics.
Well, mathematics.
That's sort of the way I think about it. Anyway, I'm a Pythagorean. So go by Pythagorean mysticism of everything is music of the spheres and so forth.
But one other topic. I thought string theory was up to 26 different dimensions now.
Sorry.
Yeah, you said the string theory was up to 10 dimensions or 11?
Yeah, 10 dimensions, but they do add more. The basic one is 10 dimensions.
Yeah, but I don't know, either way, I mean, I thought it was up to 26.
Yeah, the basic string is about 10 dimensions, I think. And then you sort of you then go for what's called M theory.
M
theory, and it adds more.
String theory has not produced an observation yet.
Yeah, well, as a Pythagorean, I see string theory as coming from Pythagoras, because he was considering the string, which is on the musical instrument, and it was vibrating, and sort of like you're getting the numbers from that. So, in string theory, it's the modern string theory. You are thinking the strings as vibrating. And so that idea goes all the way back to Pythagoras.
Well, yeah, it's actually a little deeper than that. If you remember, the Ptolemaic universe was circles within circles.
Yeah.
Right?
Yeah.
And so that is the Fourier analysis. That's Fourier analysis.
Yeah, Fourier analysis. Yeah.
Fourier analysis. And what is quantum mechanics? Well, it's Fourier analysis. You take an observation or observations, and then you apply Fourier analysis and develop your constants.
Yeah. But
that's string theory is in the end, as you look for these ways. But anything, any periodic function, any periodic reproduction can be represented by a Fourier analysis And that's, the basis of the math of not only quantum mechanics, but string theory. They're introducing everything to waves, but they're just applying the math. They're not applying what things are. They're not thinking about observations. So you look at rotation curves. For instance, you look at rotation curves, and you look at a few of them, not all of them, being more or less flat, and you start thinking about dark matter. But dark matter is rejected because there's rising rotation curves and falling rotation curves. So dark matter is rejected. But that's not the math. The math wants to keep looking at it.
Yeah. Anyway, I think it's going off topic to what Unzicker was talking about, because it's he was complaining about the Minkowski space.
Well, I don't know. That's kind of what I thought we were talking about with Minkowski, because he introduced the math first.
Yeah, so there's further development.
Before him, it was always observation and then apply math. After him, it was math first, then look for the observation. And that still exists today.
Well, I think to some extent that is Einstein's fault, because his 1905 paper
Einstein just did what Minkowski, was doing. He was looking for math. And if you look at what Einstein was doing later in his life, he was sitting around with equations and changing one variable and another, and then looking for the observation. You see? So, but that's what physics does. They look for the math first, but in the meantime, they're ignoring the observations. Look for the anomalies first.
No, I think before Einstein, they weren't doing that quite that way. So,
before Minkowski,
before Einstein, because it was more experimental physics was considered more important than theoretical physics. It was sort of like when Einstein came along, he sort of like promoted theoretical physics.
Experimental physics. Minkowski was before Einstein. Minkowski was a little before Einstein, or about the same time.
I think Minkowski was a teacher of Einstein, but he was a mathematician, so he when I read his papers when he's saying about things, he wasn't sure the physics, he was just doing the mathematics. So.
Oh, and by the way, your analogy of speed versus velocity, I think that's right. I think Einstein really was talking about the direction changing and not the speed changing. But when he talked about the speed of light,
but it's translation from German into English, and the German, it's using the same word for speed and velocity, so it gets translated differently depending on who the translator is. It's a mess. They never bothered to properly translate Einstein to make sure they got the precise meaning in English with what he was meaning in German. But Einstein kept changing his mind all the time anyway. So, okay, thank you, John. Okay, thank you. Thanks for the input. Let's see who else we got. Okay, thank you. Bye. Let's see. Okay, we move. I think Vladimir put his hand up at one time. Let's see. Is it Vladimir? Did you put your hand up? Yes. Add to stage. Right. Hi, Vladimir. Okay.
Hi, Roger. I would like to make a few comments on very interesting talk today. And let me remind you some results I talked already about in my first presentation about Maxwell's equations in details. First of all, Weber and Kohlrausch measured electrodynamic constant C in 1857. Maxwell wrote his equations in 1861, 4 years later. He calculated, based on electrodynamic constant C, he calculated the speed of electromagnetic waves. And he found that this speed, calculated based on electrodynamic constant, is close to the speed of light measured earlier. But what is important? He put his equations and he showed that in any medium with relative magnetic and electric constants, the speed of electromagnetic waves will be less than constant c. That's why there is a confusion. People, they put c as the light, so speed of light. Absolutely wrong. It is a constant, but it's a constant electrodynamic constant. In any medium, in any material, speed always less than this c. That's constant c is constant of electrodynamic constant, but it's not a speed of light. Speed of light is variable. It's better to tell not speed of light because there is no vacuum, there is no light. It is an electromagnetic waves. And he told Maxwell in his paper that based on this equivalence or close enough to numbers, he supposed that light is electromagnetic phenomenon. That's it. He didn't put in his Maxwell equations c as the speed of light. It's now contemporary physicists don't know anything about history of Maxwell equations, and they put instead of c electrodynamic constant, they put speed of light. It's absolutely wrong. I told in details in my first presentation. I want to go to the next step. The next step is space and time. Of course, space is different, time is different. It's totally different entities. That's why look at 3D space and to look at time as a parameter, as some kind of notion, some kind of, I will tell you about time in the right way. Maybe in a week I will talk about it. But what is important? Yes. In a week, I will have my next presentation, and I will talk about space and time a little bit more next week. But what is important? I do like this idea of Unzicker about these fundamental constants. Let me tell you that my model, based on two parameters only, one of them is a constant, alpha, that is a dimensional Rydberg constant, and the other one is time varying quantity Q. And that's it. All the model, what I proposed, it's based on two parameters only. There are no H, there are no C, there is nothing. They're all dimensionless parameters may be calculated based on two parameters only, alpha and Q, with different combinations, in different powers. But what is important? This is only two parameters of the model. And this is the advantage of any model, to minimize the number of fundamental constants, as I've done in my model. That's why, this is a very important point too. That's why, I'm confused. Our contemporary physicists, they don't know history of physics. We forgot so many great ideas. Every time I'm opening a new genius guys who opened the galaxies, who opened these, electrodynamic constants and all this stuff. I don't know why we don't know history of physics, and we must give our students in all universities, first of all, history of physics, the development of ideas, and then to see what is going on now. What is important? I absolutely agree that physics is experimental science, experimental. We must first of all measure something, and then to find the mathematical expressions, how to express these results. On the contrary, the last 100 years, because of special relativity, general relativity, we became mathematicians. We forgot about physics. We are doing all mathematical equations, and then we are trying to find some conclusion, some results in our physics confirming these mathematical expressions. It's absolutely wrong approach. First of all, generate ideas. Show what is new, what you observe, and then try to explain it in one picture. I'm absolutely sure with this approach. That's why I would like to return our physics, classical physics, on the right rails. You're absolutely right. We moved out of the rails of physics. We have moved to mathematics. It's absolutely wrong. Classical physics, it's experimental science. Please come back to experiments with GWST, to some other astronomical, and then try to explain what you observe, not what you guess. 100 years ago, when Einstein he proposed his equations and all this stuff, he didn't know anything about astronomy, because at that time, Hubble and that's it, who knew something about astronomy. That's why he invented something based on nothing. Now we have so many observations, so many results. Let's come back to the real physics, to the real experimental science. That's why, please, let's change our mind. Let's stop mathematical explanation, mathematical, rotations from one idea to another idea. Because, of course, so-named speed of light, it's variable. That's why Einstein was absolutely right. You cannot explain gravitational lensing without this point. But gravitational lens, we know with thousands already of them. We use this for measuring of masses of even dark matter galaxies. Dark matter galaxies, they have lensing effect, but without the speed of light variable, we cannot explain it. But we know that there is. Why we stopped? Why we didn't stop talking about this constant speed of light? Its invention 100 years ago. We must stop all this talks about it. If there are electromagnetic waves, there is a maximum, inachievable, a maximum of speed of light equals to c, because any medium, even the medium of our world, has relative magnetic parameter more than one. And I put it in my presentation. Even it's a measured parameter. It's a 10 to the minus 10, more than one, but it's more than one. It means it's not equal one. That's why the speed of light is not c. It's already based on observations less than c. That's why we must stop it. It's my point. And I will continue my ideas next week. All of you, I invite you to my next presentation. But let's return to classical experimental physics. Thank you so much for your patience. I want to know, thank you very much, because I want to come back to the genius people. They were 100 years ago, and they stopped about them talking about, and were talking about only equations instead of real ideas and real physics. Thank you so much. Hello?
You muted yourself, Roger. Unmute yourself.
Okay. My cursor doesn't seem to be working properly now.
I'd just like to point out that there are some substances where the speed of light is greater than c, if the light is traveling through those substances.
Yeah.
Yeah.
Whereas Vladimir seems to say that can't happen.
Oh, yeah. Yeah. Okay. Yes. Yeah. I don't think we didn't go into that issue. I think that those experiments are sort of argued about, aren't they? there are people who claim done experiments where they've got speeds greater than light speed c, and it ends up with a lot of arguing
because the index of refraction can be greater than 1.
Yeah. Yeah. Okay. Okay. Yeah. So, so that was your point. Do you have anything else to say? Is that it?
Well, a man by the name of Professor Harold Willis Milnes has written a paper where he has experimentally demonstrated that electromagnetic at integral velocities of light, like twice c, 3c, and 4c. And if anyone's interested, I can send him a copy of that paper via a PDF file.
Okay. Okay. Yeah, you send it to you're on the email list, aren't you? So send it to that for us people that are interested. Okay, is that it? Thank you. Is that it?
Yeah.
Anything else? That's it. Okay, thank you. Thank you,
You're
Dennis.
welcome.
Cheers. Let's see. I'm having problems here with my cursor now. So let's see. This is these are the slides. So the problem we were trying to point out is Minkowski light speed c just becomes a conversion factor, and that's not treating light speed the same way as what Einstein was originally saying in 1905, and doesn't seem to be how Einstein was talking about it later in general relativity. Well, in some parts of general relativity, he seems to be talking about light speed being c as variable, and other parts Einstein seems to be confusing things again. We've got James there. Anybody else want to talk? I did have Stephen Gift in the comments saying he wanted to say something. Is this? Oh. There. I did have Stephen Gift saying he wanted to make a comment. I don't know if he's still there. If you want to make a comment or come into the green room, I'll try to deal with it. No. Anybody can put their hand up in the green room. No. Remove the studio. Yeah. Oh, who's that? It's Stephen is joining. Right, at the stage. Yes, Stephen.
Yes, I am. Good morning. Are you able to hear me, Roger?
Yes, thank you. I can hear you. Okay. Are you going to talk about the video, or are we going to bring up a point about something else?
Okay, just a minute. I think I have a little problem.
Yeah. Right. Oh, Stephen's gone. He's going to have to try to log in again. I am. I think Ian's pointed out that the people in the comments section, if they can say if they want to make a point of the discussion or the video or anything, because most of the time they seem to be just talking among themselves. You can sort of like make it clear if you're not talking among yourselves. So Question says, why aren't space and time things? They exist even though they aren't physical. Difficult. How do you define physical? Let's see. No, my cursor is playing up. Okay. So I know he's putting their hand up in the green room, and Stephen's not coming back, so he's not back yet anyway. No. So if Stephen's not coming back, I could close the session earlier. I think I've covered everything. He's back. Stephen's back. All right.
Yes.
Hi,
yes.
Stephen.
Good morning. Good morning to you, Roger, and good morning
to
afternoon everyone.
For me.
Looking on. Yes, I was having some difficulty there, but I managed to overcome that. Yeah, I wanted to just comment, excuse me, on the matter of mathematics in physics.
Yeah.
I heard various comments this morning. The last one from your last speaker, he actually said to stop mathematical explanations and go back to experimental science.
Yeah.
Well, while I agree that contemporary science has gone overboard, they've gone too far with the mathematics and have left out a lot of the experimental work. I think going back to experimental work to the exclusion or reducing the emphasis on mathematics is not a good idea. Both are important. I want to emphasize both are important. So what is the scientific method, as we all know? The scientific method say you make observations. So that's where the experiments come in, or you make astronomical observations or whatever the observations may be, and you collect some data. Then you try to codify that data, usually in the form of a mathematical model of some sort. Then you use that model to make predictions, and then you go and test those predictions. So even though I think I agree that physicists probably more than anyone else have gone too far with the mathematics to the exclusion of the experiments, the mathematical models are essential to confirm the correctness of your ideas and to allow you to make predictions. And the predictive factor is of extreme importance. You know, when they predict the existence of a particle, when Maxwell predicted the existence of electromagnetic radiation, when Newton predicted that the planets move around the sun with this inverse square law, those are all based on mathematics. A mathematical model makes a prediction, and you test the prediction. So in my view, and that is what I have done, as you know, Roger, and I have shared it with that email group, with our email group, that it is, in my case, Celery's transformation. And I know that's not the topic this morning, but it's germane to the point that I'm making, which is that Celery developed this model, and I have used that model make predictions, and I have tested those predictions with the whole full set of space-time results and experiments that are available today. And that is essential. And you know that I have disagreement, for instance, with Nick. I think Nick is on there this morning. About
he's gone now.
He's gone, yeah. He has a tendency to speak about, to make qualitative arguments. And while those are important, you know, you want to be able to organize your thinking and to express your ideas. Confirmation of those qualitatively expressed ideas must come by way of using the analysis so that you are sure that what you are saying, what you are conceiving of, is correct. So the mathematics is important, along with the experimental confirmation of those mathematical predictions. So in closing, I'm emphasizing that the mathematics along with the experiments are both are important in making progress in and conducting meaningful and fruitful research in today's world. We can't simply go back to experiments and stay there. But I agree that the physicists have gone too far, and they have almost to the exclusion of the experiments. They have gone, they make these excursions into advanced mathematics and so on. No, I'm saying have a balance, have both, and proceed, and we are likely to get meaningful results. Thank you.
Thank you. Cheers. Yeah. So as well as the mathematics and experiments and so forth, the problem I find is trying to understand what is meant by Einstein's relativity, because you've got these ideas added to it, like Minkowski space-time, and that's what Einstein was originally including in his 1905 special relativity paper. So you're getting all these extra things added to it, and it becomes unclear as to what precisely special relativity is and what general relativity is, and how do you get from special relativity to general relativity. And so a lot of it, from my perspective, is trying to understand what's being said. And so when you've got the mathematics, it's trying to understand what's that mathematics supposed to mean, and then you can trace that bit of mathematics with what another bit of mathematics, and you're saying to yourself, is this supposed to be part of the same theory or not? Because you've got Einstein, he's saying things, and it's not clear if he's allowing certain mathematics or not. So first of all, it's sort of like he's got the transformations, which are Lorentz transformations, and then it's explained later on how that connects to Galilean transformations. And then if you bring in other mathematics like the Sorelli transformations, it's not clear to me whether Einstein is allowing those transformations in his theory of relativity or not. So the theory is just not properly defined.
Roger, are you still hearing me?
Yeah, I can hear you. Yeah.
Yeah, Roger, it's not for Einstein to allow or not allow. You know, that's not how it works. Science develops by you publishing your work and others critiquing it and making their own contributions and so on.
Yeah.
It's not for any one person to allow or not allow. And as I've emphasized in the past, the theory is over 100 years old now, special relativity. Yeah. And what has happened is that the community of physicists have more or less distilled out and agreed upon a collection of ideas which they call special relativity, which you will find in the books. I've made that point, repeated it to you. You can go to the textbooks and you can find a written out explanation or indication of what special relativity is. And there's no need that you may go back to the 1905 paper to enjoy yourself or for historical reasons, but there is a clear statement of special relativity today. I just know it has several problems in it. you know, the paradoxes and all of that. But there's no lack of clarity in the definition of what special relativity is, Roger.
I don't find it's a clear statement of what special relativity is in the science literature or in the science textbooks. I don't find it's a clear statement of what special relativity is. It just seems to be
there is, Roger. You're looking at the wrong books. I will recommend some books. I will recommend some books for you, Roger.
I think you recommended books, and I've looked at some of those books, and then you look at those books, and you can look at other books, and they say something else.
No, there's a clear statement, Roger. Roger, you're lost in the history. Come to the modern world. Special relativity is well defined. That is not the issue. It is just that it is wrong, but it is well defined.
I'm sorry, I don't think it's well defined.
Okay,
because I look at it from a historical context,
and that's the problem that you have. Theories evolve over time.
And I know they do. I know theories evolve and they change, but how that change has come about is not very clear. And it's sort of you've had this sort of Einstein saying certain things, and then you've got other people coming into relativity, and they seem to say something else. And then you got others coming in saying something else.
You're looking at the wrong people. All the internet stuff that you see, a lot of it is wrong.
There's a lot.
Go to accepted, published textbooks, Roger. It's there. You know, there's one by Costas, published Springer 2016. His first name is Costas. He has a long surname. He has it's a very well-written book on special relativity.
Yeah.
Check that book out. I'll send the name to you after. And there are others.
I mean, I don't see that they proved that their version of relativity is the correct one.
But they don't have to prove it. It has become accepted across the community of physicists, Roger. That's how it works. Well, so you see these books get referenced to, you see these books get cited repeatedly, like the book by Rindler. Rindler has done a lot of work. Resnick, French. Those are standard books that are repeatedly cited. So people accept those versions as the correct versions and representation of special relativity.
If you go back to Galileo, as I see the person who you get in modern physics from, he was a minority point of view. The existing point of view for what we call physics now was from Aristotle, and Galileo was going against that point of view. So you've got minority point of view, you've got majority point of view, all believing one thing, and I would call that the mainstream. And then you got the minority point of view, which I would call the alternative physics people. So you've got the mainstream point of view of physics, and you've got the alternative physics point of view. And I don't go with the majority point of view. I go with the minority point of view. And so when it comes to looking at what the mainstream physics people are saying, I want them to prove to me that their version of relativity is the correct one. And from the reading of the literature that I see, they don't prove that. There's just lots of lit books on relativity, and that I can point to that book says so and so, and that other book says something else, and they all contradict each other. And I don't see that any of those books prove that their point of view of relativity is the correct one. That
Roger, they don't prove. It doesn't work like that.
I know they don't. They just
work like when they prove. There's a community that accepts and cites the work.
Yeah, but I don't see how that community comes to their decision, how they reason through that they want to interpret relativity in a certain way. Yeah. I don't see how they do that. It doesn't seem to make any sense, because I go by a minority point of view, and the main person I'm going by is a Dr. Lowe, and his point of view is Einstein's relativity has been completely misunderstood, and he's written many papers on this, and he's sent me a draft of his book now, And he's pointing out that things like the equivalence principle have been completely misunderstood. So you can go to a standard book on relativity explaining to you the relativity principle, but Dr. Lowe was saying no, that book has completely misunderstood what has been meant by the equivalence principle, and they've got it all wrong. And he does connect to doing experiments for how he interprets that. And so it still goes back to the mainstream. That's sort of like the majority point of view. They haven't proven why they have decided to believe what they believe. And you can go to a minority point of views when they write their papers, and you say, well, with those minority point of views, they're right, and it's the majority that has all gone wrong. And as classic example, Galileo is pretty much the lone man, the minority of one, the majority of everybody else. They're saying completely opposite to him, and the minority point of view was correct in that instance. And so I just keep looking at things from the Galileo point of view, that the minority point of view is right, and the majority haven't properly explained themselves, and the majority need to prove things, and they haven't. So
okay,
that's the way I look at it.
Sure. Thanks for letting me
so that's how I look at it.
Yes,
so
thank you very much.
The majority are wrong.
Yeah.
And
thanks a lot.
And they haven't properly explained, the majority haven't properly explained relativity. They've changed it and so forth, and it's not a properly defined theory anymore, because you get the experts in relativity and they contradict themselves. And I've been to the celebrations of Einstein's relativity, and those people there are very, when they're given their talks, they've given their points of view on relativity, and as far as I can tell, they're just contradicting one another. They're saying I'm an expert on relativity, and another person says I'm an expert on relativity, and they contradict.
Okay. Thanks.
Thank you, Stephen. Okay,
take care. Stefan.
Cheers.
Yeah.
Thank you. Bye.
Okay.
I think I saw another hand come up, so thank you, Stephen.
Yeah.
Any other hands? I think we're running out of time now. Okay. I think that's. Anybody want to put their hand up again? Yes. Add to stage, Vladimir. Okay. I think we're running out of time.
One very small comment. First of all, I absolutely agree with Stefan about the mathematics and physics. I'm not talking about to exclude mathematics. It's absolutely wrong. Of course, we need her. Physics cannot survive without mathematics. And based on a simple mathematics I developed in my model, I've done many predictions that were confirmed later. I calculated gravitational parameter, Hubble parameter, temperature of microwave background radiation, and all this stuff, and so on and so on. That's why his approach to mathematics and physics coincides with my approach. That's why, but what should be the first? First of all, should be some experiments, and try to explain them in frames of your model. And then if you need to correct model, correct it. Or if you have some predictions, do it, and then wait when observations will confirm your predictions. Thank you so much. Okay. And thank you very much for a very interesting session today.
Thank you.
Have a good day.
Guys. Yeah.
Okay, bye now.
Thank you. All right. Thank you, Vladimir, and thanks everybody. I think we've run out of time now, just when we're heating up the conversation a bit. So thank you, everybody who's contributed, and I hope you're interested in what has been presented about Minkowski space-time. And we're ending session now. Thank you.